A simple pendulum. A simple pendulum consists of a metallic ball called bob, hung by a perfectly inextensible and weightless string. When a bob is at rest position in a straight line, it is in its mean position. When the bob is displaced from its mean position and then released, it makes to and fro movement about its mean position. If the pendulum moves from one extreme position to the other and back to the first, it is said to have performed one oscillation. Time period. The time period of a simple pendulum is defined as the time required by the pendulum to complete one oscillation. Frequency. The frequency of the simple pendulum is defined as the number of oscillations performed per unit time. The length of a simple pendulum is the length from the point of suspension from the center of the ball. Let us perform an experiment to observe that the time period varies with the length of the pendulum. Number 1. Suspend the bob by a perfectly inextensible and weightless string. Number 2. Measure the length of the string from point of suspension and the center of the bob. Number 3. Gently pull the bob pendulum from one extreme end in such a way that it moves from one extreme position to the other and back to the first. Number 4. Take a stopwatch and record the time a pendulum takes to complete 10 oscillations. Number 5. Time period of simple pendulum will be time taken to complete 10 oscillations divided by number of oscillations. Number 6. Repeat the process with different length of pendulum. Number 7. Plot the graph with time on x-axis and length on y-axis. You will get a curve graph. Number 9. From this graph, we infer that time period varies with the length of the
Okay, I think
pendulum.
thank you, sir. The video is not really like it's not seamless like I thought it should be. Yeah, thank you. Let me see how best I can explain. And I think they went to secondary school, so they will understand when I sketch. Right. So guys, let's get started. Please, I want your imagination to be sharpened this morning. You're going to imagine a lot because this is a topic that you need to see the experiments to understand proper. So let's look at your simple harmonic motion. Now, if you have questions here, always talk. But I'm going to assume that you, in your secondary school, that you did experiments. If you didn't do the experiments, then you need to go and collect your school fees from anybody or any school that you attended. Right? Yes. But I think I did a lot of experiments back in my own school. We did a lot of experiments. Right? By the way, I am Mr. Hillary attended the same secondary school, but he left us midway. Yeah. So let's continue. All right. So we have simple harmonic motion. So people that you met during the boot camp, you guys can do a lot together, right? You guys can do a lot. Just like I and Mr. Hillary have been working close together for quite some time now. All right. So imagine your simple harmonic motion, right? So for this okay, let's just imagine this phenomenon that we have right here. Now you have this one. This is mass. This is mass on the spring, right? Mass on the spring. Now this is your simple pendulum. It's suspended using your, what do you call this very stand now? We'll call it, I can't remember the name. You have a stand You can remember your
Retorts.
experiment. And then, aha, retorts. Titi Lola, the scientist. You are doing well. All right. So now you have the retort stand and you have your pendulum board suspended on that, right? Now, that said, if you observe, when I know even if you didn't do this thing in school, some of us that played so much, if you have a spring, when you draw it, let's say with this mass now, you pull this mass down, what will happen? It will then go right, it will go up, down, up, down, up, down, up, down, up, down, right? Just that way. If you watch this movie, Three Idiots, when the guy was told to explain what a simple machine is, he was using a zip. He was saying up, down. When you draw your zip up, down. I know you guys didn't watch that movie. Find time to watch. It's a very interesting movie that has to do with science, engineering, and creativity when it comes to technology, right? It's an old movie, actually. So now you draw this, when you draw this mat downwards, what happens here is that the spring will move up, down, up, down. Do you understand what I'm saying? The two is going to dangle. Give me a thumbs up if you're following. When you pull this mass down, right, it's going to bounce up, down, up, down. Beautiful. Richard, I think you played very well when you were much younger. The way you are giving the thumbs up there. So it goes up, down, right? Now, remember that the more you pull this, like the more you pull this weight, what happens? The further the distance you pull it, the more dangling you're going to get. I will call it oscillation after now, but let me just use a layman term. The more it dangles, is that also? The more you pull this guy. Ibaja, you're giving me thumbs up. You didn't play when you were much younger. Go outside and play with any child you see there. You understand it. So when you pull this guy, the more you pull, the more distance, the more displacement you pull. Ibaja, what's the problem? You're going to just follow. You're going to understand. The more you pull, the further the distance you pull it, the more effect is going to dangle. It's going to take a long time for you to settle down, right? Now also observe this one. And here, simple pendulum, good for people that attended class. So you have this one now. This simple pendulum, back then they will tell you guys to use your watch, right? You have your stopwatch. And back then in my secondary school, the girls in our class, they always fight for the time. I want to hold the time. They don't even know how to press start, some of them. So back then you have this clock, you have this pendulum. So somebody will time it. Once you press start, before you move this thing up here, you're going to press start, and then you start going to and fro, So remember that the more, then some of those guys in my class that are very, very mischievous, the guy will pull this thing so far, like, normally you don't have to pull it so much. The further you pull it, the longer it takes for you to stop. So some of those guys are going to take this thing so far, the thing will keep moving and moving that under 5 minutes, you are still doing one experiment. Something you should just put a little bit. So what am I saying? The further the distance you put this, the more time it takes this guy to keep moving to and fro. Do you understand now? Are we together? So you see that the motion is going to be repeating itself. It's going to be repeating itself. So this is what we call a periodic motion. Is actually a motion that repeats itself. So you're going to see that this guy will be repeating itself, including this one as well. They'll be repeating themselves, right? And that kind of motion is what we regard as what? As periodic motion. Now, one thing you have to remember that as much as this guy, when you pull this guy, please follow me, men and brethren. Women of Jerusalem, follow me. Men of Jerusalem, follow me as well. So now, the more you pull this guy, the more you pull this very guy, right, the more time it takes to come back. And he must always come back to this center, right? Because when the ball is at rest, it is at the center before you now pull it, including this very mass. It will be at rest before you pull it, right? Now, that position where it is at rest before you pull it is what we call the equilibrium position. You can call it equilibrium position. You can call it the fixed position. You can call it the rest position. A thumbs up if you are still following me now. A thumbs up if you are still following me now. So that position at which it is at rest, Ibaja, a thumbs up. Are you following now? Stephanie. All right, Stephanie Ibaja. Beautiful. Well done, Stephanie. So now that is what you regard as your rest position or your fixed point or your equilibrium position. Now, when you pull this guy down, what happens? The ball bounces up and down. You're going to see that the acceleration of that object will always be directed towards the equilibrium position. It will always be directed towards that rest position, because if I pull it, it still returns back up and down towards that equilibrium position, which means that the acceleration of that object will be opposite to the displacement. I am pulling the guy down this way, but when it starts moving, it keeps going back to the equilibrium position. So the acceleration of the object will always be, right? It's going to be what? It's going to be what? Opposite to the to the displacement, right? And that acceleration is directly proportional to the displacement, right? The acceleration will be proportional to the displacement. What does it mean? The higher the displacement, that the more you pull it from its original position, the more it accelerates, right? The higher the acceleration. The lower the displacement, that the lower you pull this very much, the lower the acceleration. And that acceleration is always opposite to the displacement. I want to be speaking like a white man from now onward, isn't it? So let's proceed. Now, the next thing I want you to know about is that simple harmonic motion is periodic. Simple harmonic motion is what? A periodic motion. That means a motion that does what? Repeats itself. Now, remember that this one is the left-hand side is mass on the spring. So we're going to consider two cases. Case one will be mass on a spring. These are the things that they test you on as long as your simple pendulum is concerned. So we have our case one about your periodic motion. Case one is mass on the spring or mass suspended on a spring, mass on a spring. That's our case one. Now, case two is that experiment you did back in secondary school. And I'm wondering what some of you look like in your secondary school uniform. Now, the next one is your case two. So for case two is your simple pendulum. Maybe I'm going to do a challenge next week. Post yourself with your secondary school uniform. Is your simple pendulum. All right. So let's proceed. I said something that your simple harmonic motion is a periodic motion. So a periodic motion is a motion that repeats itself. It repeats itself, just like what I explained, up and down motion of those things. Now, and I said something about the acceleration of the object, that acceleration is directed towards the equilibrium position, right? So now, but before the equilibrium position, I want to say something that you will have the equilibrium position. So we'll have this very concept. The next thing I want to speak about is your equilibrium position, right? So equilibrium position is more like the resting point of the particle. So the resting point of the particle, or the rest point, which one is correct? So the resting point, I'm teaching you physics, not English anyway. So the resting point of the particle, resting point of the particle is regarded as what? As the rest position. Or you can also regard it as the what? Equilibrium position. All right. So that said, regarding this, now I was making reference to the acceleration, and I want to write a few things about the acceleration as a working document for us all. So I said acceleration of an object of the object is directed, acceleration of the particle or the object. Let me call it object so it will make more sense to us. Acceleration of the object is directed towards the equilibrium position. All right. Is directed towards the equilibrium position. Now, and it's always opposite, right? Right? It is opposite to the displacement. Opposite to the displacement. So these are key things I want you to know about the acceleration, right? So let's actually express something. When I pull this guy down, when I pull it down, let's say I pull it down here, this will be my displacement when I pull it down from the original position. Let's say here is x, right? So this side now, if you see the distance here, the distance from here to here, right? This is your x as well. That's your displacement. So, but for this one, it's going to be y because displacement is actually in the vertical component. All right. So, and the acceleration of the object is always directed towards the equilibrium position, opposite to the what? Displacement, right? And the acceleration is directed towards that fixed point. Is that okay? Equilibrium position is that fixed point, and it's always directed towards that fixed point. Now, the next statement I want to make is regarding what I said, that the acceleration is directly proportional to what? Acceleration is directly proportional to the displacement. Acceleration is directly proportional to the displacement. Don't mind my spelling. Once I hit now, I'm going to be active. Proportional to the displacement, right? So let me make a rough sketch that might not be so perfect. Let me draw like the same way that Titi will draw. So let's have this. Let's have this line. Yeah, I know people that cannot draw actually. I know Rachel can draw. She sounds like somebody that can draw. She does sound like that. But you see people like him, so I know them. Then I think Nikki Gold Silver can draw as well. All right, so you have this. Is she in the class? Okay, maybe she went to do delivery. All right. So now, when you pull this object downwards, interesting. Let's say we'll displace this object down. We'll displace this. We'll displace this down. If it's your hobby, please try and draw Paul for us and send it to the group chat. So now, the acceleration is going to go the other way around. You have your acceleration pointing upwards this way, right? So this is the displacement in the y direction. So now, the further I pull this, the further I pull this, right, the more it accelerates. I believe that concept I've stick to your head. I know why I'm repeating this thing. I'm saying acceleration is proportional to displacement. I keep saying it. There's a reason for that, right? Because everything revolves around you understanding that the more you pull it, the more it travels. And that acceleration will always come back to the rest position. Remember that here is our rest position, guys. Always remember that this place here that the object is currently, this is our what? Equilibrium position. Is our equilibrium position. All right, a thumbs up so that I can proceed. A thumbs up so I can proceed. All right. So now, what this simply implies, thank you, confidential confidence. You're doing well. Rachel, a thumbs down. You are confused? Are you confused? Oh, Susan. All right. So look at what I said. It's quite direct, right? It's quite direct. Look at what I'm saying. Now imagine you have a rubber now, like some of you that can be very wicked sometimes. Let's say you have a rubber band. This is a rubber band, and the rubber band has cut, like let's say it's in has cut somewhere here. So when it cuts, it becomes something like this. Now, and you want to actually use that on someone. So the more you stretch this rubber, the more you stretch it, the more the pain at the back of the person's neck. Give me a thumbs up now, Rachel and Susan. The more you stretch the rope, the more the pain on the person's neck. Rachel, are you following now? Susan, are you following now? So the more you stretch, the more the pain. Now, that stretching, as you are stretching it, even your catapult, as you are stretching it, stretching your hand. I wish my video is on. I'll be going back to my workspace hopefully by tomorrow. I've not been there for quite some time because of some issues, light issues in particular. So now, when you stretch that very rope, this topic would have been better if you are seeing me. When you stretch that very rope, the more you stretch that rope, the more the displacement, right? That stretching is the displacement. It also happens in flogging. If someone is flogging you and the person raises the hand very high, that person want to kill you. So because the higher the person raises his hand, that's the more the displacement and the more the pain that comes from the cane. So that's what we're trying to say here now. Let's bring it back home now. That the more I stretch this, like this is the weight now, this is a spring. The more I pull this spring, the more the acceleration is going to dangle so much. One, just like when the cane is, when you raise your hand very high, when that person brings that back down the hand, the kind of pain you're going to feel will not be compared to when the person doesn't raise the hand. So that's the same thing here. When I draw this thing so much, it's going to dangle up and down, up and down, up and down, up very fast at a very high speed, accelerating so much. So that's why I said that the more you pull it, the more the displacement, the more the acceleration. And the acceleration is going to be opposite to the pulling. You pull it this way, the body moves the other way. Everybody, Rachel and Susan that gave me a thumbs down. Does it make sense now? Yeah, thank you for that love emoji. Kai, I don't get love emoji this morning. This week will be very good for me. Thank you, Father. All right, so let's proceed. We have our equilibrium position. If you will not understand why I'm always happy when I get love emoji, only if you will understand. People that view my status, that's the only people that will understand better. All right, so people like me that view my status and I think anointed and poor, they will understand better. All right. Titi, okay, Titi can relate as well. So now let's continue. Now, what that simply means is that the higher the acceleration, like I said, right? The higher the displacement, the higher the displacement, the higher the displacement, the higher the displacement. You know, this is not scientific. Like this is not how it should be written on a normal day. But for us to understand better, the higher the displacement, the higher the acceleration. And remember that acceleration is always in the opposite direction to that displacement because acceleration and displacement are vector quantities. Is that also? They are both vectors. And because they are vectors, you have to put into consideration the direction. So when you pull displacement to the right-hand side, to the down part, acceleration is going to travel up towards the fixed position, right? At every point in time, it's going to travel towards the fixed position. So now, what is now simple harmonic motion? You know that simple harmonic motion is a periodic motion, which means it repeats itself, right? And its acceleration is what directed towards a fixed point, and it is proportional to the displacement from its equilibrium position. So now, what are we saying right here? We are saying that your SHM, right? SHM, please, I don't want anybody to feel behind, is a very critical topic, and they ask a lot of this question. If you check your past question, you can give me a thumbs up if I'm correct regarding simple harmonic motion. That they ask questions from there a lot. If you check your past question, you can give me a thumbs up if I'm correct. It is a periodic motion of a body. The periodic motion of a body in which its acceleration is directed. The acceleration is directed towards a fixed point. Is directed towards a fixed point. What is that fixed point? The fixed point is your equilibrium position. The equilibrium position, right? And it is proportional. It is proportional to the displacement. It is proportional to the displacement from its equilibrium position. Paul, do well to look for questions for us as always. Paul, are you on the call, brother?
Yes, sir.
All right. As always, my bro. All right. So now mathematically, you're going to have that the acceleration is equal to minus omega squared. Then that W is omega. I don't know how to put that omega symbol from my own end. So let's have this, or let's use red so we can actually make emphasis on that very formula. So this will be my first equation for today, though I'm not going to use it so much, but just take note of that. And this is our equation number one. Now, where W is your angular velocity, W equal to your omega, not W actually. Omega is your angular velocity. Of course, you can tell that X is equal to your displacement. Remember that if it is for case one, this should be Y, is that not so? Because case one is your mass on a spring because it's going to be a vertical displacement. Is that not so? But if it is your simple pendulum, it's going to be, are we together, guys? If it's your simple pendulum, it's going to be an X. If you get my point, give me a thumbs up based on what I just said. If you're working with mass on a spring, it's going to be Y. You're working with simple pendulum, it's going to be X. Oh, beautiful, guys. Beautiful, guys. So now that is what it is now. This symbol, the negative sign, is telling you that the acceleration is opposite to the displacement. That negative sign simply attesting to the direction of what of your acceleration, because acceleration is opposite to the displacement. Remember that both of them are vector quantities, and because they are vector quantities, it is expected that the direction of acceleration is going to be opposite to the direction of the displacement, as you've also seen from the experiment. All right, so there are key things we have to look at. What are those quantities, or what are those terms that will make use of a simple harmonic motion? Just like when you come to the house, we have different names for different persons. Your one of your siblings will have a particular name, and there's also a name that you guys call him or her at home. So that means these are the terms that we need to know as long as simple harmonic motion is concerned. So let's look at the terms of SHM. Now, before I start writing anything, I want to use those images to actually explain what this term is all about so that it will make more sense to us. Now, let's go back to my secondary school. I was a good student back in secondary school anyway. The only thing is that I talked so much and I played a lot back in secondary school. And they saw that I deceived others. That's what they normally say. I deceive others, but I never knew what it means to deceive people. All right, so let's go back to my secondary school. Now, during these experiments, the ladies back then will take note of the time using their stopwatch. Now, someone like me will now pull this from the original position back to this place, right? I'll just displace it a bit. Now, before immediately I pull it to this place, we'll start recording our time. Is that also? So we'll start counting the time it takes you to move to and fro, like to and fro. So now, if it moves from that very place, that very my displacement, which is here, it moves from here, goes to here, and comes back here. That is one cycle. That is what one cycle. That is one oscillation. So the time it takes this my pendulum bob to complete one oscillation is what we regard as the period. So I spoke about the very first quantity that we know as period. You know, so this word happens a lot even in school, first period, second period, the word period have been used a lot of time, someone can take, I've told you, period, like, so, but for now, this is what, for your physics, you also encounter that in wave, right? But it's a word that even when you are shouting to somebody, you want to tell that, I'm not giving you, some of those things, use that word a lot, right? So now it's simply telling you the time it will take for you to complete your one cycle. So also for this, our friend, if I carry this my mat and displace it downwards, if I pull it here, the time it will take this guy, right, to move from that down part, to move up, down, just up and down to that place I started, is what we regard as your what? We regard it as your what? The period, right? So the time it takes you to complete one cycle. Does that make sense, brethren? If it does, can you give me a thumbs up? All right. All right. All right. Thank you, Titi, for that thumbs up. Thank you. All right. Rachel for that thumbs up as well. You guys are doing well. For the guys in the house, Anointed, Paul, Chinon. So are you guys following? A thumbs up from one of you. Okay, beautiful, my guys. Yeah, you guys are the best. So now, period. But then the guys, you guys didn't do well yesterday. Yesterday was for the ladies. None of you said, "Oh, let's do giveaway for them at least 500 naira airtime." You know, that's how to be a responsible man. You know, but none of you did that. That's very bad. I'm talking to Paul and the rest. You guys should contribute to 200 naira. That should be 600, and send airtime to them on the group and tell them happy International Women's Day. That's how it is done. Okay. All right. So the time taken for a body, but I trust my guys. I know they will do it. A thumbs up, guys. Emmanuel go talk say he never chop, he won't buy airtime. Okay. I said he's laughing. So the time taken for a body to complete one oscillation. Be checking my spelling of this oscillation. Or maybe I'm spelling OC instead of oscillation. Oscillation, that is Y cycle. I think that my spelling is wrong. You guys can correct please. It's wrong. Or someone should correct me, please. Type on the chat so I can copy it from there. Time taking for a cycle to complete one oscillation or vibration. Oh, people that went to good secondary school. You won't blame me. They taught me physics with Igbo language. They taught me physics with English, with Igbo. So you don't blame me that I don't know how to spell those things. So right, you have the time taken for a body to complete one oscillation. Right, that's your period. So mathematically, it simply means that period that's T equal to time all over what? Your oscillations. So that said, mathematically, you have that T is equal to the time taken to complete one oscillation, then N, and it is measured in seconds. So this will be our second equation for today. And all of these things are going to come handy when we start solving questions together. This is the second equation. Now, after period, right, sorry, please include that it is measured in seconds, guys. This is my equation number 2. So let's write measured in seconds. All right. Now, the next one is what we'll call your frequency. So now the frequency, when we stretch this thing up, is more like your consistency. Let me relate it to your reading. Your frequency. You read today, you read tomorrow, next tomorrow, you are consistent. And the more you read, the more you know. Right? The more you read, the more you know. That's your frequency. Another way I can actually put it up is the more you come to your friend's house, the more you stop being a visitor. And the day they will tell you to go and wash plates, that shows you that you're no longer a visitor in that house. So because you keep visiting them, your frequency has increased in the house, and they now see you as a family member, right? So let's apply that to the frequency of your equilibrium position. So now, if you stretch this thing down, the number of times, number of oscillation it takes, up, down, up, down, up, down, up, down. So the number of oscillations is what will require measured in hertz actually, made in a second, is what we regard as what? Frequency. So number of oscillations per second, right? So if you move up, down, you record the oscillation. One up, down, up, down, up, down. So that number of up, down motion, that's to and fro motion. If you are still working with this guy, the number of move from here to this place, 1, from here to this place, 2, you know, that kind of thing. From here, return back, go again, return back. So that number of oscillation per second, you know, is what we regard as what? Your frequency. Does that make sense? If you want to forget, remember the examples I gave about reading and the examples I gave about visiting your friend. So the second quantity, Titilola, you are confused. What's the challenge, please? Okay. So when you are confused, always remember the examples I gave a bit in terms of how frequent you visit something, right? Even in your statistics, you did your mode, highest occurring frequency. So this is simply the number of oscillations number of oscillations made in a second. Right? And it is measured in hertz. All right, very interesting topic, guys. Now, so your frequency F is simply telling you you are accounting for the number of oscillations, per time. So mathematically, for some of us that are very conversant with wave, should have seen this equation somewhere. So F is equal to N all over T. Now, let this be my equation number 3. Yeah, the wave lord, Sister Lillian Wave, has given us a thumbs up. So this is equation number 3. Sorry. All right, this is your equation number 3. But I want somebody to observe something between equation number 2 and equation number 3. Someone that has an eye that doesn't drink so much Gary can actually, I don't want anyone that drinks Gary to say anything. So check and see that there's a relationship between equation 2 and equation 3. Can someone observe something? There is something happening between equation 2 and equation 3. Equation 3, if you invert equation 1, you're going to get equation number 3, right? So do 1 over t is going to give you n over t, right? So from equation 3, Rachel, you're not giving me a thumbs up. Or maybe you are part of those that drink. Okay. So from equation 3, thank God I didn't say that before you sue me to court. So from equation number 3, we have that from equation 2, we have we taking reciprocal of it. Okay. I think I need to go and do spelling and dictation again. I don't know what is going on. So I'm going to have 1 over, if I invert it, 1 over t, I should have n over t, right? And you could see that this part of the equation, you would see something interesting, that this side of the equation is going to give us what? It's going to give us what? Our frequency. So, brethren, that implies that your frequency, just like you must have seen it from your wave, that frequency is 1 all over t. And I'm going to call this my equation number 4. Please take note of all these tiny details. And as you take note of that, I pray that your effort is going to pay off. That's if you are putting effort anyway. So that's your equation number 4. We've linked both equations together. Now, the next one I want to talk about is what we call your amplitude. Now, what is your amplitude? Now, your amplitude is the maximum displacement. So when you hold your mouth, people can, like I said, so if you want to do something very bad, you can hold your mouth so tight, like you can bite the tip of your mouth, hold it so tight and pull this, right? So when you pull it, the highest point it can get to in terms of your stretching is your maximum displacement. Every human being has a maximum displacement. There's a particular limit of something you can condone. And if somebody crosses that maximum displacement, you're going to serve it the person hot. You're going to serve it, and then you spark like naked wire, especially for our people, Good. So you have your maximum displacement. That's the most that someone can stretch you, the most that you can condone, the most you can take. That's the same thing about this. So the highest point you can get to while stretching this, like if you stretch it, right, that point for here now, here is our maximum displacement is the value of the distance from here to here will be our maximum. because from our diagram, that's where it stopped, right? So that the maximum displacement is what we regard as amplitude. But remember that we have different x values here. Let me establish this, right? You have different x value here. From here to here is also x. Is that also? From here to here is also x. From here to here is also x. Then from here to here is now the maximum x. A thumbs up if you understand what I just said. Yeah, so there are different x values, but the maximum x is what we regard as your amplitude. Okay, so the next one, number 3, is your amplitude. That has to do with the maximum displacement of that object. So amplitude, right? Amplitude. You can also apply amplitude to your spring, right? Not only the what do you call it? Because I'm handling 2 cases. Also, for this one, it has a maximum displacement. When I put this guy so down here, that's the highest, right? Depending on, it can vary depending on how you pull it, right? So anywhere you stop, that's your maximum displacement, depending on you, how far you stretch your hand, So for that reason, we said that our maximum amplitude is simply the maximum displacement a body undergoes in a simple harmonic motion. So this is the maximum displacement. This is the maximum displacement, right, of a body undergoing. I hope I can spell this undergoing. Okay, undergoing a simple harmonic motion. So that's your amplitude, right? So the next one I want to talk about is your angular velocity. When you are traveling in a straight line, you say linear velocity, right? On a straight line, just like we did for momentum, and when we studied our motion, we are talking about what? A straight line. Does it make sense? But when you now talk about you moving around a circle, right? So you are now, instead of measuring how fast it moves per second, you now measure how fast the angle changes, right? So let me quickly make a statement for our people right here to understand better. So now, when you're talking about moving in a straight line, right, you're talking about linear velocity. But when you start talking about things like this, moving around an angle, moving around a circle, I should have introduced circular motion before now, but I feel that this one will take more time. That's why I'm doing simple harmonic motion. If there's time, I can now talk circular motion. That one is a bit direct. So now, your angular velocity simply describe how fast something rotates around the circle, as compared to your linear velocity that tells you the distance you cover per unit time, right? This one is telling you the angle you cover per unit time, right? So for linear velocity is equal to what? Linear velocity will give you what? Displacement over time. But for your angular velocity, it's going to be what? Angular displacement. Amount of angle you cover per time, right? So your linear velocity is measuring how fast you are moving per second. But for angular velocity, we measure how fast the angle is changing. Let's say we start from here, right? You are revolving around, you get to this point, right? We are trying to know how fast is your angle changing per time. How fast is your angle changing per time? That is what your angular velocity is all about. So for linear velocity, how fast your distance changes. And for angular velocity, how fast the angle changes. So it's a matter of the changing from V to what? To your omega. Give me a thumbs up if you understand what I'm saying now, right? Give me a thumbs up if you get what I'm saying. Beautiful. Now, when a body completes one cycle, if you move through a circle and complete it, your angle anytime you go through a full cycle is equal to 360 degrees. So for your cycle, your theta, what am I trying to say? All of this thing I'm drawing here for your angular velocity, I think I should go somewhere here to talk about it, right? I should go somewhere here to talk about the diagram. So now imagine I'm moving around a circle, like I said. So how fast your angle changes is your angular velocity. So imagine journeying through and you complete the cycle. The angle, actually, your angular velocity, remember that linear velocity is what? V equal to your displacement over time. Angular velocity omega is equal to what? Angular displacement all over time. This one is how fast, right? How fast your distance changes, how fast your angle changes. Now, if you complete one cycle, your theta is equal to 360 degrees. But in physics, we don't like making use of degrees. We make use of radian. So in radian, you're going to have that 360 degrees is equal to 2 pi, because 180 degrees will give you 1 pi. So that means that theta is equal to 2 pi. That's the angular displacement when you rotate or complete a cycle for a full circle, right? Is that okay, guys? Does that make sense, everybody? You've seen the difference between your linear velocity and angular velocity. Beautiful. So, yeah, I like the thumbs up. Rachel, you're not giving me a thumbs up. What happened? Are you confused? Please.
Yes, I'm actually confused.
Okay, sorry. What is confusing you? Is it the circle?
You say that one cycle is 360, right?
Yes.
But can it be called one revolution?
One revolution. One revolution. You know, when you start talking about when you
Okay.
start talking about revolution, it's a different ball game. You know, there's a difference between rotation. I think it's a different ball game, and revolution.
Okay.
Yes. I think it's a different ball game. You know, it's a different ball game actually, right? Uh, okay. It can as well go, right? It can as well go. Yeah, I think it can.
Okay.
Yes. So when you I think that's a very good question there, right? So it can as well go. Sorry, I said it's a different ball game. It can as well go, right? So imagine that if I start from here, one revolution of a circle, when I move from here and return back to where I started from, that's one revolution. Do you understand now?
Okay.
Yeah. So one rotation, one revolution is 360. Rachel, you sabi book, I beg. Thank you for tilting my head to that direction. Right. So one revolution, one rotation, yeah, 360 degrees. Well done. One revolution, 360 degrees. Yeah. Well done. So which means that, thank you for that powerful question, which means that this number of oscillations here, are we together, guys, can also be written as what? Number of revolutions. Number of revolutions. Yeah, I like people that think out of the box. That's a good one. I think you ate pounded yam this morning. It must have contributed to this insight. So you have number of revolutions, right? And yeah, that's it. So frequency, number of revolutions over time over oscillation. So this is time over the number of oscillation. This is also revolutions. Yeah, thanks a lot. So when you start from a particular point and you move 360, that is also your revolution. So one complete revolution should give you your 360, right? So round a circle, I start from here, I move through, and I return to that point again. So one revolution, let me put it down. So one revolution, one rev is equal to 360 degrees. So one rev, a revolution is also equal to 2 pi degree, 2 pi in radians. Everybody now on the same page. Everybody on the same page. Everybody the same page. All right. So now let's talk about the concept that brought me to this side. I was trying to explain my angular velocity. So let's talk about that concept that brought about your angular velocity. All right. So now for angular velocity and everything around this, our question is that some of the things they'll be asking us to get the angular velocity of a mass suspended on a spring, angular velocity of simple pendulum, you know, of a pendulum bulb attached to your redox stand and the rest of them, and also the period. All of those things are things that will be required of us. So now angular velocity, like I said, is the same thing as linear velocity, but this time around, you are moving around a circle. So you have your angular velocity. So this describes, in a layman term, this describes how fast This describes how fast something rotates around a circle. Around a circle. Right? Just like linear velocity. Linear velocity. Be reading this and I'm writing in case I make mistakes in my spelling on the right. Just like linear velocity will measures how fast. It measures how fast. Yes. An object moves per second. The angular velocity it measures how fast the angle changes. The angle changes. So our angular velocity omega is equal to angular displacement. Angular displacement always represented as theta divided by time. So that W, mathematically, W is equal to theta all over T. This is our equation what? Let me see those that are following me. This is our equation what?
5.
Yeah, makes it. Okay. Yeah, 5. I have people following. The boys are no longer following. When I don't go for pot to help the stomach. This is equation number 5. All right. So now in one revolution, right? Remember that T is angular displacement T, and the units, please, units. It is measured in radian. Please don't put it in degrees. Don't allow your village people to cause you to leave it in degrees. It is measured in what? In radian. All right. Now, it is important to note by that, just like our friend said, one full revolution, just like Rachel has pointed to us, and equal to 360 degrees. That is that one revolution, one full revolution is equal to what? 2 pi. This is in degrees. This is in radians. Right. Okay, Rachel has raised her hands up. Rachel, go ahead and express and tell us what you have for us, please. Go ahead. The stage is yours.
Okay, it's actually a question though.
All right, go ahead, please.
I was watching a video in the YouTube and they said that 1 rad is 180, but 2 rad is
Yes.
50. How come?
Okay, that's a good question as well. So now, let's say one Titi Lola, Titi will say, what did I do to this man? So let's say that one Titi is 180. Now, 2 Titi now is equal to X. So that means that X is equal to what? 180 times 2. So X is equal to 360 degrees. So if 1, good, Titi. So that's what happened right there. So that's why you have, if 1 is 180, 2 will now be 2 times 180, that's 360. So 1 full revolution is 2 radian. All right, so let's proceed. Richard, I hope that's clear now, right? All right. Beautiful. Now, what do we need to do right here? Please, you need to put on your seatbelt now. There's this kind of dance we want to do now, the dance of equations. We'll be connecting a lot of things now. Just put on your seatbelt and brace for impact. Now, at this 360 now, it simply means that after one complete revolution, that's if I complete one cycle, right? One cycle, you're going to have that theta. So for one cycle, for both cases, right? For that, your mass on the spring, right? And your simple pendulum, in bracket, mass on spring, slash your simple pendulum, mass on spring and simple pendulum. What that entails or what that implies is that we have that theta is equal to what? 2 pi. Therefore, we have W will be equal to, right, 2 pi all over. Now, I want to do something before I do this. Now, recall, so I don't confuse anybody, that angular velocity theta is equal to what? T over small t. But for one cycle, we have that t is equal to t. That is the period. Recall that period, it doesn't make sense, guys. Good. Richard, your hand is still up.
That's a mistake, so
I have a mistake. Okay.
I said
I
that's
get it. Okay. It's the time taken to complete. Let's go back to that place I explained period. Time take for a body to complete what? One cycle or oscillation or revolution. To complete one cycle. Right? Therefore, anointed, are you following? Follow. All right. So W, right. See now, so. Okay. I was thinking maybe you don't go hustling. So now is equal to, it will not be what? 2 pi. I'm here. Okay, beautiful. Well done, bro. Full attention, okay? 2 pi all over t. So once it has completed one cycle or one revolution, Rachel, look what we're going to do. Click on that hand again so it can go down. So I know when you have question and when you don't have question. Just tap on that hand again. Oscillate your hand back again. Good. All right. So now that said, we have a new equation, and that should be our equation number 6. Is that
6.
also? Yeah, beautiful. Yeah. One. All right. So that said, okay, Titi.
Like the equations we've gotten at they are 7. I believe that are rubbish.
I saw I didn't hear you, Titi. Can you please come again?
I think the equations are 7 because we have an equation for amplitude, but nobody counted that one.
Okay. No, equation for amplitude is this one, actually. Angular displacement over time. That's the fifth one, measured in radians. Then I broke down that this same angular displacement, when you have completed one cycle, what happens is that the angular velocity now reduces to equation number 6.
Okay, sir. Also, that
Yeah, it's okay. Okay. Susie, is that's how they call it at home, Abi? Susan, what's the problem? Are you having headache? Stephen,
No.
you're not constant in the class. You are just coming and going like Nigerian NEPA. You just come and go, come and go. So that's why you're a bit confused.
Size
Sir,
So
network.
what you said? One person at a time, please.
I said it's network
So
that
who,
is disturbing.
okay, network is disturbing you. So you gave me a thumbs down. You are confused.
Yes, just for this recall, this upside now.
Okay, which one is the upside? There is plenty up here now.
It's time taking.
sir, my own
Again,
angwa and
Susan, talk so I can hear you. See, Susan, say your own is what?
angular velocity. Are you
Okay, okay. So I said that angular velocity. Now pay attention. Stephanie, sorry, yeah, Ibaja, pay attention. The other person pay attention as well. So you can actually, anything you know can also go down. Now, let's say this is your younger brother. What's his name? Susan. Oh, is my voice still cracking now? Okay, their voice is cracking, right? Or is it my own voice? Confirm you can hear me, everyone.
network?
Okay, okay. So let me repeat their question. So guys, their question is that they are a bit confused regarding the angular velocity. So I want to explain something. Okay, I want to explain something. Let's assume that this is Susan. Okay, let's say this is Susan here. Now, your younger brother now took your meat. I know Susan will like meat. And then this is your house. This is your house. And as he took that meat, he was just running around the house. And you are busy shouting his name. My meat, oh, my meat, oh, my meat, oh. You are chasing your brother around, you know. So you guys are traveling around a circle. As you are pursuing your brother, you guys are going through a circular path. Now, as you're moving that circular path, because the guy is very brutal, sometimes he will run like this and shake his head the other way, while you will pass, you know. So when he shakes his head, you are going to move like this. You take this part. Why the guy continues through a circle, and he's doing that. He's eating the meat. Now, what happens right there is that your angular velocity is no longer measuring. Assuming he's running on a straight line, that means it is linear velocity. But since that guy is very brutal, he's going through a circle. You can relate to this, right? That's all. Since the guy is very brutal, he's running around a circle. Now, what we are going to measure is his angular velocity, the way his angle is changing per time. How fast the guy is changing angle. Because the angle here and the angle at this point here will not be the same. So your angular velocity has to do with what? Changing how fast your angle is changing. But linear velocity is telling you how fast, how much distance you are covering per time. But this one is in terms of the change of angle. Does it make sense now? Now, the formula for linear velocity, right, is simply what? Velocity is what? Distance over time. Angular velocity now is now measuring the change in your angle over time. This angle is called angular displacement. Now, and if your brother started running from this point, let's say this is where he took the meat from. When your brother runs and runs and covers and returns back to that point where he took that meat from, and because you are not too strong, you now fell or you fell down while running, you know. So he now got to that point and started resting here. So that is what one complete revolution. So your brother, I mean to say, has completed one revolution. And because he has completed one revolution, the angle theta now is equal to what? 360 degrees. Remember your mathematics, angle at a point. Now, but since your angular velocity is measured in radian, we'll have that theta will be equal to 2 pi. Because in radian, 180 degrees is equal to pi. Now, therefore, we still have that angular velocity is theta over t, but now theta is equal to 2 pi because he has completed one revolution. Now, bringing it back to what we did on mass and what we did on simple pendulum, we said that your period t is the time it takes to complete one cycle. up and down. So the time it takes your brother to run from here back to this place, that time is what we call the period, t. So therefore, your small t will now be what? Capital T. So therefore, your angular velocity after he has completed one cycle will now be equal to what? 2t all over 2 pi over t. But the angular velocity as he is traveling at every point in time, when he was here, to calculate the angular velocity here, you just use what? Theta over t. The one here, theta over t. But when he runs and returns back to that point again, that angular velocity will now be what? 2 pi over t. Does it make sense now, Susan? Does it make sense now, Ibaja? A thumbs up if it does. Thank you. Ibaja, does it make sense now? Beautiful. And for other persons that we are here before that understood, I think it makes more sense to you now. All right. So that says that gave birth to our equation number 2. Yeah, thank you for the love emoji. Can you give me one more, please? Just one more. Thank you. All right. Let's continue, my people. Okay. So now we are one great family. Yeah, we're one great family. So we have W equal to 2 pi over T. All right. So let's see how we can connect all of these things together now. We've connected it to your period. I will say that W equal to 2 pi over T. So now what this formula gives you, right? This formula, men and brethren, will give you the relation, right? Relation between, let me use short form, between angular velocity and period. So which means we've related the equations angular velocity to our what? To our period, right? That is what that very guy does for us. Also, men and brethren, also recall, don't worry, when we start applying the formulas, it will make more sense. But I want us to understand the whole of this concept so we can actually apply our formulas. Also, you know why? If you understand all of this trick now, there's nothing jam that will do that will not understand because you know where the formula is coming from. Also, recall that f equal to 1 over t. Which equation was that? That I said that f is 1 over t. That was from equation number 4. Recall from equation 4. So from equation 4, yes. Now plug again. I will plug in Mango here. So plug equation 4 into, sorry sir for deviating, but we are taught in school that the radius is half of a diameter. We are taught in school that the radius, sorry, well, he said, sir, sorry for deviating, but we are taught in school that the radius is half of a diameter and diameter is equal to 120. Why did 2 pi become 260 instead of 4 pi? Interesting. Now, can you quickly call the person that taught you in school and ask him why he said that, why didn't you ask him about this 2 pi back in school? All right, so now it has nothing to do with diameter. Yes, your teacher was correct when he said that diameter, radius is half of a diameter. Yes. And no, diameter is not 180. So its diameter is different now. We're not talking about diameter now. We're talking about the angle. So your teacher was very correct when he said that diameter is equal to the radius is diameter divided by 2. But that 180 is not diameter, is angle. Does that make sense now? It's more like converting from radian to degrees, not about diameter at this point. So they are different ballgame altogether. Is that okay? So plug equation 4 into equation 6. I'm trying to look for a perfect example for you to understand what I'm saying. Good. It's more like converting from good. Emmanuel, It's more like you converting from when we learned precision, we said that 10 millimeter will give us 1 meter. Do you understand it now? It's more like a conversion factor. That way, 180 degrees is equal to pi. Not about diameter, it's about conversion. A thumbs up if you understand what I'm saying now. So we can move to the next thing, please. Good. So plug equation 4 into Ferami. I've seen you are in the class. That's why you gave me a thumbs up. Thank you for showing me you're in class. So now plug equation 4 into 6. Welcome, okay? Glad to have you. And I've not been mentioning your name all this while. Forgive me. I never knew you joined the class. All right. So when you plug equation 4 into 6, remember that equation 6 is like this. W equal to 2 pi all over 1 times 1 over t. I can split the equation like this. Nothing has changed, people of God. Is that not so? Nothing has changed. Has anything changed? No, nothing has changed. So anywhere I see 1 over t, I will plug in f, right? So that implies that I have that w, in that case, sorry for using the wrong ink. So that means that w is equal to w is equal to 2 pi f. If you believe what I said, give me a thumbs up. So that will give birth to equation number 7. All right. People are following. People of God are following. Good. Makes sense. Now, how do we now get the angular velocity for these cases? Angular velocity for your pendulum system, angular velocity for your, what do you call it? Angular velocity for what? For simple pendulum, and angular velocity for mass on a spring. How do we go about estimating those ones? All right, so give me 2 seconds. Let me get something, please, while you take a little break as well. Now you can go ahead and check up on 1 or 2 persons. Just 2 minutes to do that. All right, welcome back, guys. We are back from the commercial break. So welcome, everyone. Now, the next task we have now, I thought you guys would give me a love emoji as you just came back from the commercial break. And nobody's doing that. All right, thank you. I think I should be coming to class with basket so that I can be packing this love, and then I will withdraw it during the day, when I don't see anyone coming. So let's go. We have our angular velocity equal to 2 pi f at this point. The next thing that we need is, how do we now connect? All these things are coming from angular velocity. Now we've seen the formula for angular velocity on a normal day. We've related that to our frequency. We've also related that to our period as well. So this is equation number what? 7. And 7 has to do with what? Is it 7 or 8? Yeah, 6, 7. So this is our relation between between angular velocity and frequency. Richard, you are giving me a thumbs down. What happened? All right. So next one is let's talk about angular velocity for mass, right, on a spring. So let me call it number 5, right? Angular velocity for mass on a spring. So that formula for mass on a spring, you have that omega. No, what I did was, you see, remember that, let me explain. She said she's confused. Richard says she's confused about equation 7. Remember that frequency is equal to 1 over t. Now, I simplified equation 6. And if you simplify equation 6, you're going to see something when you simplify equation 6. So that simplification for equation 6, you're going to have that 2 pi over 1 times 1 over t. So 1 over t is what? F. So I plug in F right here. So this is 2 pi. W equal to 2 pi F, equation 7. Yeah, I believe you understand it now. Thumbs up if you do. All right. Instead of a thumbs up, she gave me a love emoji, guys. Did you see that? All right. So we'll have that omega. It's equal to, you have your square root. Paul, why are you laughing? You and them mess up. So that's the square root of k all over m, right? So k, they will give you the spring constant. K is the spring constant, and m is the mass of the body or the object. All right, then this happens to be my equation number 8. So that's how you get the angular velocity for that object that is on the spring, right? K is the spring constant, which is always given, right? So this is equation number 8. Are we together? But then remember that we can link, we can get the period. What else can I do? All right, so I think I'll do that one differently, right? Before I talk about linear velocity for your periodic motion, so you can know the formula for that. All right, I think I've done a lot today. 15 minutes to stop so that you guys can have time to revise whatever thing we've done. Right, so this is for your spring. Then let's look at angular velocity for simple pendulum. So the 6th one, right? 6th one, angular velocity. No, not about too much equations, right? They are all connected. They are all connected. So for me, I'll give a summary. Don't worry. I'll give a summary. You are not cramming anything, okay? The equations are all connected. Yeah. Thank you for the thumbs up. Angular velocity for simple motion. I'm going to show you something. They are all connected. And I'll tell you the ones I want to always remember. All right. So that will be W. Sorry, omega. Yeah, I saw the fear. I had to speak immediately. Omega is equal to the square root of G. I'm just documenting them so it will make more sense to you. When I start solving problems, you see that it's not a big deal, right? I'm just trying to document the equations so that L, and you're not cramming anything, they're all related. L is the length of pendulum bulb. That's the length of that thread that is holding the pendulum. Then G is acceleration due to gravity. So finally, I'll just show you the key equations you have to remember anyway. It's just for us to document it. It's not a big deal, actually. It's not a big deal because this material, you guys are still going to have access to it. So I'm trying to make it as direct as possible. So we'll have number 9. So now, so far, what am I trying to say? What are the key things we need to remember, right? So let's do a little recap before we continue. Now, what are we saying? Now, recap now. We are saying that we have what we call your period, right? And we said that your period is simply what? Number of oscillations over time, right? The time required to complete one oscillation, right? That was what we talked about, your period, right? So we have time over oscillation. So we say that period is simply time over number of oscillations, which we regarded as t. They will say that frequency is simply the number of oscillation over time, and that is simply what we introduce r to be what? 1 over what? Over t. Now I brought about your angular velocity, which is theta over t. But when it completes one cycle, it becomes what? 2 pi over t. Now, if you can remember that 1 over t is f, you should also know that if you plug in that w is equal to 2 pi f. So when you record this one, if you can record this one, recall what the period means, recall what frequency is all about, recall what angular velocity is. Other ones are just direct. If I can remember what's the meaning of period, means time over number of oscillation, frequency, number of oscillations per time. So time required to complete one cycle. This one is your angular velocity. Then if I complete one cycle, I'm bringing these two guys inside the equation. When I complete 2 cycles, I'm bringing these 2 guys. So you know that in terms of period and in terms of frequency, that will give you your angular velocity. Do you understand it now? And finally, the one you need to now cram or remember as JAMB is concerned is this formula now to get angular velocity for mass on a spring, and to get this is the one you need to remember, and to get angular velocity for this guy. Do you understand it now? Also now, good. Titi Lola, are you still here? Titi, are you still here? Good. So now there's one more thing I want to link now, right? How do we estimate your period? How do we estimate period for those 2 cases, right? How do we estimate period for those 2 cases? Still the same thing. You're not cramming a new formula, right? See the same thing. See the same thing. How do we estimate that now? So let's see. Period. Susan, you're not saying anything again. Susan, are you still here? You've not mentioned that you are confused or anything. Hope you are following. Anyway. Okay, interesting. So for mass on a spring, we'll have that W is equal to K over M. Just understand the process where the formulas are coming from. K over M. But remember that W is equal to 2 pi all over T. How do we estimate period for mass of a spring? So that means I have that 2 pi over T is equal to square root of K all over M. So what next? I know some of you that don't know mass, that is where this thing will start shaking you people, sha. But I don't want to still go. I don't want to go straight and give you guys formula. Let's just see how the thing came to be. So I'm trying to make T the subject of. You said? Hello?
I don't know. Square both sides.
Okay, I'm looking for T. Is it your time? Are you sure? Let's do that. The square root. Okay, let's try. First of all, let's do 2 pi is equal to T. What I want to make subject formula is T. I want to make T the subject formula. So I don't think you need to square anything at the moment. So now to make T, yeah. To make t subject, I'm going to divide both sides by k and m. So it's going to be what? T will now be equal to 2 pi divided by square root of k over m. So that t will now be equal to what? 2 pi. When you are dividing, you're going to invert your denominators now. Is that also? You're going to have square root of m over k. So that t is equal to 2 pi square root m over k. So this one will give you the relationship between your period, how to get the period for mass on a spring. Is it confusing? Is it confusing? Is it confusing? A thumbs up if you are following. A thumbs up if you are following. All right. Now, the assignment I want you to do for me now, get for me the period for a pendulum system using the formulas we've estimated. How do I now get the period for a pendulum system? Now, the idea I'm going to give you is that make use of this, that W is equal to root G over L. Then find the W, which is 2 pi over T. Then make T subject of formula to get the relationship of period and your simple pendulum. Do you understand what I said? A thumbs up if you understood what I just said. Iba, relax first. I know you, even before now, I'm going to explain to you. I'm talking about those that said yes in the first thing I did. People that said yes before now, before I explain for her. Oh, everybody's giving me a thumbs down. Now look at what I'm saying, eh? We've established something. We have the angular velocity for a simple pendulum, which you should remember actually. That formula must be remembered. You also have the angular velocity for mass on a spring. Now I'm trying to see how you can calculate the period from here. How you can relate the period to these very variables for your simple pendulum. These are the key variables for simple pendulum. So how do we relate? Because simple harmonic motion is simply you are getting. I should have taught you guys circular motion first, because simple harmonic motion is an offshoot of circular motion. So we're trying to relate that information of circular motion to our mass and to our spring. We're trying to connect our circular motion to them. So now this is angular velocity from your circular motion, and then these are the variables for simple pendulum, the gram and the length of the pendulum. So how do I calculate the period? That's the time it takes the pendulum to complete one cycle. Like, how do I calculate the time that it takes the simple pendulum to complete one cycle? And how are we going to do that? We've estimated something that for one cycle, for your circular motion, that one cycle will be 2 pi over T. So now when I plug in W now, 2 pi over T, I can easily now calculate for T by making T the subject of formula. So I plugged in, I have 2 pi over T equal to K over M. Now what I'm looking for is how do I make T to stand on its own? Coefficient of T is K over M. So I'm going to divide both sides by K over M. So that's why I did 2 pi divided by K over M. It will cancel out. You have only T. Now in mathematics, when you are dividing, you invert. You bring multiplication and the denominators are going to invert. And when you do that, you're going to estimate that the time to complete one cycle for a mass on spring is this. This is the time to complete one cycle for mass on the spring. Now, and I said, go ahead and now estimate from this information you know about the angular velocity for angular velocity for a simple pendulum. Now, I want you to find the equation that will give us the time requires to complete one cycle for simple pendulum. And that is the period for simple pendulum. Remember that W is 2 pi over T. Then make T the subject of the formula so you can have an equation connecting your period for your simple pendulum. Does that make sense now? Does it make sense now? Nobody's responding. Can it make sense? Does it make sense now? Can it? Does it make sense now? A thumbs up. A thumbs up. Yeah. Why are you still confused now? What's happening, guys? Look at what I'm saying. You learned about your circular motion. For circular motion gives you key things. Circular motion teaches you about your angular velocity. Are you paying attention now? Circular motion teaches you about your angular velocity, which is theta over t. Now, we want to relate this angular velocity to what? To your simple harmonic motion. And what are the variables that we'll talk about in simple harmonic motion? Is the period, the time it takes that pendulum bob and the mass to complete one cycle. The frequency, which is the number of cycles it makes per second. These are the two variables we want to estimate for our simple pendulum. Also, we want to estimate the angular velocity for a simple pendulum and for a mass on a spring. These are the two things that gives birth to your simple harmonic motion. Now, we've established that this is this for circular motion. But then, these guys, which is your simple harmonic motion, they are dealing with what? They deal with what? A pendulum bob and a mass of spring moving to and fro. So for us to estimate to and fro, we have to talk about the time it takes it to complete one cycle. And for us to be able to do that, we've established that this is what we know as our angular velocity for somebody traveling through a circle. Therefore, for one complete cycle, we said that W is equal to 2 pi t, 2 pi over t, and W as well is equal to 2 pi f for one complete cycle. So this is what relates our angular velocity to simple harmonic motion as regarding your period and frequency, which is the key thing about simple harmonic motion. Completing one cycle and knowing the number of cycles per second. Now, that said, we now have a formula that can help us calculate the angular velocity of a body undergoing simple harmonic motion. We said that if the mass is suspended, then our formula is simply k over m. Now, if the body is undergoing is a pendulum, we said that W is equal to what? G over L. These are key variables about your mass on spring. These are variables about your simple pendulum. And we are now saying, based on that, how then do we get the period? That's the time it takes to complete one cycle in relation to these variables now, related to these variables. And I solved simple mathematics. If I have that W, I think your problem is mathematics, is square root of km. Now, W is equal to 2 pi all over t. So I have 2 pi t equal to square root of k all over m. Now, you cross multiply. You have that 2 pi is equal to t square root of k over m. Make t the subject of the formula. Make t subject of the formula. How do you make t to stand alone? Is it not divide both sides by the coefficient of t? By the coefficient of t. And when you do, you're going to have 2 pi divided by square root of k over m is equal to t, because this guy will divide itself and it's going to give us only t. Now, that said, when you are dividing, young people, a over b divided by c over d is equal to a over b times d over c. You invert the denominator and change your division to multiplication. That's what you learned in maths back in secondary school. And that's what I'm going to apply right here. So therefore, you have that 2 pi times square root of m over k is equal to your period. So the period for a mass on spring is going to be this, m over k. That's the formula. But if you cannot derive it, just cram it. All you need to know is how to apply the formula. So if you cannot derive, cram it, that the formula you need to estimate the period and the variables of a mass and spring is this formula. Now, I gave you an assignment to go and derive the formula that will be used to solve for the period for a simple pendulum. But it's entirely fine if you cannot prove it, you cannot derive it, just cram it. But for me, I think if you can remember the derivation, even when you forget the formula, you can always find a way around it. Does that make sense now? Titi Lola and Steven, sorry, and uh, now if you don't understand it, don't stress yourself. Give me a thumbs up. Actually, I can explain again, but I feel that yeah. Steven is a mathematics problem. Okay, it's a mathematics problem. Yeah, it's a mathematics problem. So it's a work you're going to do on your own, right? So that we can rest and attend our biology class by 2:30. So it's a mathematics problem. So do well to sit with your maths problem. Okay? Yeah. So we can rest a bit for our biology class. So that's for that, guys. And if you cannot derive the formula, it's entirely fine. Just cram it and remember that the period is the month here. So period for mass on a spring. Yeah. You don't like maths, just find a way to transfer the love you have for somebody to that one, okay? To mathematics. Yeah. I know you can relate to what I'm talking about. All right. So that's for that, guys. All the best. I hope it makes sense today, right? So, Paul, what you are going to do for me, Paul, is that when we meet our next class, let's solve more questions. But please look at these formulas again. Try solving questions on your own. You have what it takes now to answer questions on that. As much as I have not finished, but I think you have what you need to answer some of those questions. The one that might be challenging is the ones on potential energy and kinetic energy regarding this question. I'm going to do that in our next class. Yeah, Stephanie, what's the problem? Go ahead.
So, sir, please, as I do not understand it, that means I should not bother myself doing the assignment.
I didn't hear what you said, please. You said?
I say I didn't understand what you said. So, should I not bother myself doing the assignment?
Ah, is that how you learn?
Because,
That's
like,
that's not that's not that's that's not how I learn. You have classmates, meet them. You're on the group chat. Go to their DM and let them explain. Assignments will help you to understand better.
okay, I will try.
Yeah. You will try. Look at you. See, there are cases. I've seen cases where I didn't understand Let me shock you. There was a day I was in class and I was not feeling too strong and I was sleeping, right? And all of a sudden, I saw somebody like the person placed her hand on my back. I wanted to say, who is that person? I wanted to shout, like, who is that person? When I looked down, because I was bowing down, I saw that it's the leg of the lecturer. Hey! And that she was the woman that was just holding me at the back like this. Then I said I should stand up. I should go and explain if you see the kind of sleep, I should go and explain what they are teaching. I went there, they gave me the book. The first thing that left my mouth is praise the Lord. Like, I don't know where to start from, you know. But let me shock you. At the end of the day, right? I couldn't explain it. People laughed and laughed because of the way I behave sometimes, you know. So I thought that the woman laughed as well, very well. But she now said, okay, carry your book, come to the front, or yeah, leave my class. I left the class. But let me shock you. My summary was what people read to pass that very topic. I was not in her class. So I went home and did my work as normal. Do you understand? It was my summary note that the entire class read to pass that very topic that they learned, all of them did class. So it's not an excuse, you know. It's about pushing harder to understand some things. So that's the basic thing. So I wish you all the best, guys. And solve questions. Look for past questions and so. Paul, send some of them on the group chat. Paul?
Yeah?
No, I said Paul.
Okay.
Paul, send some of the questions on the group chat. Yeah. And somebody said equation now water. It's not about the equation, it's about understanding these things. The equation not be water. Paul, send some of them on the group chat.
So someone has sent some, and they are
All
part
right.
of the questions I would have sent.
Okay, interesting. All right, so all the best, guys. All the best. I'm sending the slide to the group. Any other question? Okay.
Sir,
Yeah. Yes.
we did not talk about well, okay, that is a different topic. I wanted to ask about this thing, the Central Peter Falls that moves an object that is moving in a
Yes.
circle.
Yeah, that's circular motion. Yes,
Right?
that's circular motion. That one is simple.
Okay.
It's direct. So I said, let's battle out this simple harmonic motion first. So in our next class, before I solve questions on simple harmonic motion, or as we're solving questions on simple harmonic motion, I'm going to talk the circular motion a bit. So please go to your dashboard and watch your video lessons. I wish you all the very best, guys, and I love you all from the depths of my heart till I find a replacement. All right, guys. All right, guys. All the best. Bye.